Welcome back to the Tinker-Pie Factory, everybody. We've now gone through several videos in this series to lay the groundwork for our project. In this video, we're going to put it all together and you're going to learn how to control this Arduino robot with an Android phone. We learned how to get started with the Arduino in number 19. Then we learned how to connect the HC06 Bluetooth module in number 20. In 21, we learned how to create the simplest of App Inventor Android apps. In 22 and 23, we connected that app to our Bluetooth module. Number 24 was for those of you who are using a Kindle. We had a minor hurdle to get over there. Then in number 25, we added the L298 motor driver to the mix and learned to turn it using our app. Finally, in number 26, we learned how to put together our Tinker-Pie robot. Now keep in mind, these videos will apply to any Arduino robot you may have. Like all new projects we get here at the Tinker-Pie Factory, we're going to start with a list of requirements. This is what we want our robot to do. It should be modular, meaning we want to be able to add more components to it like sensors. It should be easily controllable. It should be fairly inexpensive. And it should be easy as possible to program and modify. So based on those criteria, I decided to use the Arduino Uno because though it's not the smallest, it's usually the easiest board in the Arduino family. Because I wanted it easy to control, I choose the Android app developed using App Inventor because tilting the phone, I think, is more natural than pushing buttons, and App Inventor is super simple. All of these parts are fairly inexpensive, and the rechargeable batteries will save money in the long run. Let's open up App Inventor to where we left off in number 25. We're going to remove the test buttons. We don't need those anymore. We're going to focus on one task at a time and test as we go. Forward, left and right, reverse, left and right, stop, pivot left, and pivot right. By breaking things down, we make the project less daunting, so let's get started. As we tilt the Android forward, the y-axis increases and x remains 0. So y represents the speed of the robot and x represents how far left or right we want to go. The formula we're going to use to calculate the speed is this. Speed equals 255 times y divided by 255, where 255 is the max speed of the motors. So this means if we tilt the Android forward all the way, our speed will be 255 times 255 divided by 255, which is 255. So that's full speed. Our accelerometer will go higher than 255, but we're going to cap it off. We're going to start by focusing just on the forward direction. X is negative in the upper left quadrant. Do you remember that Cartesian plane? I know it sounds like an airplane going to a really warm place, but it's this. The more negative x is, the tighter the turn. So if you can picture what the wheels are doing in this quadrant, the right wheel is going to the speed of y, and the left wheel is going slower. How much slower is what we're going to determine using this formula. Differential equals speed minus speed times x divided by 255. I call it differential because we want to figure out the difference in speed between the wheels. The bigger the difference, the tighter the turn. So again, let's look at that extreme example where x is 0 because we want to go straight ahead. We determined that the speed is 255, so the differential would be 255 minus 255 times 1 divided by 255. We have to make all zeros a 1 because we can't divide by 0. This comes out to essentially 255. In other words, both motors full speed ahead. Let's try this again somewhere in the left quadrant. When y equals 150 and x equals minus 100, then the speed is 150 and the differential is 91.5. The reason I call them speed and differential is because the wheel you set to either value will depend on the direction you're going. The speed is always the faster wheel. Let's go ahead and program this. We're going to first remove the test buttons we used in the last step. We won't need these. Then we'll pull over an accelerometer from the sensors group. Go into Blocks View and let's move the blocks we won't be touching out of the way. We'll be using the clock and we're going to drag over the accelerometer's on change event. Next, I'll create two global variables to hold x and y values from the accelerometer. In the accelerometer's on change event, we'll set those values. One little caveat here is that the values coming from the accelerometer don't match up with the Cartesian plane as we learned during the microbit series. The plus and minus are swapped. Since 3D printers and mills also have the left as minus, right as plus, I'm going to multiply by -1 to switch them around. Next, I'm going to write these values to the labels we created in the last video. Let's test the app to see how we're doing so far. You're seeing the x-axis as I'm tilting my Kindle completely left and right. We need the range to be minus to plus 255 in a comfortable range. In other words, we don't want to have to twist our wrists around to go full speed. This is called user interface design, where you think about how your product will be used and design with that in mind. Let's go back into the app, and I'm going to set this -1 to -60. I had to play around with this number to get the range right, so we wouldn't have to spend the time here. This process often involves a lot of tweaking and testing. We'll switch back to the Android app, which should automatically update, and now we can see the numbers are more in range. So far, so good.